All right. So, here's our problem from last lesson, except I had to change it because it didn't quite work because I made a mistake, okay? So, in a titration using 25 ml of sodium hydroxide, 15 ml of acetic acid at 0.2 mole is used. What is the pH of the resulting solution? Okay. So, what's our first step whenever we're given something that's a bit wacky, we don't know what to do with it? Ben, write the equation. Okay. Now, in this case, I'm going to shorten acetic acid to HACET because the actual formula is CH3COOH with the end hydrogen being the acidic hydrogen. So I'm going to call it HACET plus what? NaOH. To form, what's going to form?
Sodium acetate.
NaAcet plus H2O. Everyone agree with that? My chemical formula, okay. All right. What's the next step? Is this titration going to its end point? I am videoing, guys. You don't need to take photos. Come down the front then. All right. So, what's the next point? What's the next step? Is this going to completion? What do we need to work out? Do we need to work out how much of something is left? Because what's going to be left over? Some acetic acid and some sodium acetate. So we need to work out how much of that there is. All right, so how are we going to work that out? No rice tables, not yet. How are we going to work this out? How much acetic acid do we have? How many moles do we have? How many moles of acetic acid do we have? No, it's 0.015 multiplied by 0.2. Right, everyone? So it's 3 times 10 to the minus 3? Yep. How much sodium hydroxide? We've got 25 ml at 0.1, so that's 2.5 times 10 to the minus 3 moles. That will give us 2.5 times 10 to the minus 3 moles of sodium acetate. Do you agree with that? Yeah?
Stephen, is this going to be like a question that's like at the end that's hard, or is this going to be like one of the basic questions that we have to know?
This is one of the questions you need to know how to do. Last year, in last year's test, I gave the students a 25-mark question, or it was a 20 or 25-mark question, based around this stuff. I'm not going to do that this year, but I'm going to put some hard questions on there. All right. How many moles of sodium hydroxide will be left at the point of the reaction, when this reaction occurs? Are we going to use all the sodium hydroxide? What's the matter, Kamaya? So, moles, moles, moles. We're going to make...
How'd you get the molarity of the NaAcetic acid?
How did I get the number of moles of acetic acid? So, I multiplied 0.015 by 0.2 to give me 3 times 10.
Like the Na...
because you know that for every mole of this you create, you're going to create 1 mole of that.
Okay.
Okay, it's a 1-to-1 molar ratio.
That's because sodium hydroxide is the limiting reagent?
Yes, so in this case sodium hydroxide is the limiting reagent, and sodium hydroxide, so we're going to use up all of our sodium hydroxide in this reaction because there is less than there is acetic acid. Does that make sense to everybody? Everyone clear on that? So let's subtract. So we subtract 2.5 times 10 to the minus 3. So there are no moles of that left. This starts out at 0. So that both these guys start out at 0. So it's actually plus 2.5 times 10 to the minus 3 plus 2.5 times 10 to the minus 3. How much? So what am I doing here, guys?
So the last bit.
Kind of. But it's not an equilibrium.
Oh my
So
god.
Rick table.
Ish, yeah.
Rick.
Okay, so what's happening here? Ben, what's happening at this point here?
We're losing 2.5 times 10 to the negative 3.
Yep.
Yeah, 5 times 10 to the minus 4 remaining.
So we're left with 5 times 10 to the minus 4 moles of acetic acid left in our solution, in our reaction vessel. Okay. So that's just a sum. Okay, got it? Yar? Right. Now, that is the number of moles we have left. Is it the concentration?
No.
No.
So what will our concentration be? So step 1 is to do this, to do your reaction. Step 2 is to work out your stoichiometric ratio. Step 3, moles remaining. Step 4 is concentration. So, John, how are we going to work out the concentration of this stuff? Of the concentration of acetic acid and the concentration of sodium acetate.
Is it like a C times D or
What's the concentration relationship, Maya?
C equals N over V.
Okay, C equals N over V. What's our volume going to be, Kamaya?
Which one?
Our volume of sodium acetate. What's our volume going to be in our reaction vessel?
The total volume in the. Is that?
40 mils?
Yeah, 40 mils. It's our total volume. So then our concentration is equal to 5.45 times 10 to the minus 4 over 0.04, and the concentration of sodium acetate will be 2.5 times 10 to the minus 3 over 0.04. So there are our concentrations. And that will be, when we work it out, 5x4 minus divided by. So that's 1.25 times 10 to the minus 2 moles per litre. And this one will be 6.25 10 to the minus 2 moles per litre. Everyone understand how I got to the point of concentration? Are there any questions?
Why using the concentration of the whole thing?
Because it's neutralised and because that's your total reaction vessel volume. Because you're going to, so that's the total volume because most of it is water. Okay? It's mostly
Measure of
water.
concentration at the end of the reaction.
Sorry?
Is that the measure of concentration of those things at the end of the reaction?
At the end of the reaction. Okay. So, I'm going to write these two concentrations up on the side of the board for the next part of what we're going to do. Is that all right with everybody? So what I'm going to say is that square bracket HACET is equal to 5 times 10 to the minus, no, sorry, 1.25 moles per litre, and then the concentration of ACET minus, because the acetate, so it's just an acetate ion because the sodium is a spectator ion. Do you know what I mean by a spectator ion?
Doesn't do anything.
Doesn't do anything, just floats around in the solution. Is equal to 6.25 times 10 to the minus 2 moles per litre. Now, what can you tell me already at this point about what our pH will potentially be? Is it going to be acidic or basic?
Acidic.
Acidic. Let's work it out. Okay. So what's our next? So
Acetate's a proton receptor.
our next step is to look at what happens when acetic acid dissociates, because we're looking for the pH when the acetic acid dissociates. Okay? So I'm going to erase this portion of the board. So the next step is to look at write a dissociation equation. So we've got HACET plus H2O is going to form acetate ions plus H plus. Understand? Yep. Yar. And we know that our Ka is 1.8 times 10 to the minus 5. So our dissociation equation is that. What's the next step? The next step is to put it into, so to then work out what our Ka would be equal to. So if we write it out, Ka is equal to our products, so the concentration of ACET minus multiplied by the concentration of H plus over the concentration of the acetic acid.
Don't we need to balance it?
Why would we need to balance it?
Because there's 3 hydrogen on the left and there's 1 on the right.
So that's the same as, so what we're saying is that's the same as saying that plus H2O.
Oh, okay.
And because H2O doesn't, we're saying it's the concentration of the hydronium ions in solution. All good? What do we do next? What- We know Ka,
And you just like solve for H plus.
Yeah.
and we solve for H plus.
Wait, were we given Ka?
And then you
We are given Ka, it's up at the top there.
can take the log and find pH.
So we can do that. I just want to make sure we just we rearrange and substitute in. So How do we, let's rearrange before we do our substitution. Why are we rearranging before substituting?
Just less likely to screw it up.
Yep, it's easier for the marker to see where you've made a mistake. Okay, so we're going to say concentration of H plus is equal to the Ka multiplied by the concentration of HA set all over the concentration of A set minus. And that makes sense to us, doesn't it? Because what we're saying is that the Ka multiplied by the amount of acetic acid we've got
That's how
is
much
that
it's associated.
that's how much it's associated, and we're taking into account the amount of conjugate base as well at the same time.
Yeah, okay.
Does that make sense to everybody? Because that conjugate base will react against that. Okay? So then we substitute in our values. So we say that 1.8 times 10 to the minus 5 multiplied by 1.25 times 10 to the minus 2 all over 6.25 times 10 to the minus 2 is going to give us our concentration of hydrogen ions. And if we substitute that into our calculators, multiplied by 2.5 x 2 minus divided by 6.25 x 2 minus gives us 3.6 times 10
3.6 times 10 to the minus 6.
10 to the minus 6.
That's what I got.
And then what's the next step from there?
Take a negative base 10 log.
Take the log of it. So log,
What is this log thing we're talking about?
log. And then you do, so you do minus log of 3.6 times 10 to the minus 6
Minus.
gives us pH.
Oh, really?
5 point.
That wasn't actually super.
5.44.
Is that the final answer that we need? Or
That would be the final answer that you need at the end of the titration.
That's actually not too bad.
Ben,
No,
you right?
yeah.
Okay. Can I make this mildly more complicated
No.
now?
No, actually, I do have a question.
Yes.
So with the Ka,
Yep.
acetic acid, you just had, you were given that.
Yes.
You didn't figure that out.
No, you were given that.
It's like
It's a constant.
okay.
Okay?
So how did we figure out the concentration of the acetate?
The acetate ions,
Yeah, the 6.25.
6.25. We took the concentration of, we took the number of moles left and divided by 40 mils.
We did.
Yeah, but wasn't that
C
for
equals
the
N
Na
over three.
acetate and
So Na acetate is the same as acetate minus. The sodium is a spectator ion.
Wait, how do we know? How do we know? Wait, I'm confused.
Okay. Are you all confused or not?
To get the concentration of just the acetate, like, but we use the whole thing, didn't we? Because we did 2.5 times 10 to the minus 3, but we used
The whole, the total volume, because most of it is water and it's been diluted.
we use
sodium acetate, we didn't just do acetate.
Yeah, but sodium acetate and acetate, same thing.
Do we, because for each mole of
Because
sodium acetate, you
there's
get
an
a mole of
acetate
sodium
and a mole of acetate, and they're going to dissociate. Okay?
So, could you say that you would have like, so So 6.25 times 10 to the minus 2, you're gonna have like 6.25 times 10 to the minus 2 moles of acetate.
Yep.
And moles of sodium?
Yep.
Okay.
Okay. Let's make this let's look at a titration curve. So where would this be if I've got a curve, if we've got a titration curve, if we have pH here and we have mils H acet here. Okay, so we start at 0, we go to 14. Where does our titration start? Does it start here and go up, or does it start here and go down?
Wouldn't it start acidic?
So you start with sodium hydroxide and you're adding.
So you start with sodium hydroxide in your flask,
Oh.
So it started higher.
starts higher, so this is where the top of our titration is. Where is the equivalence point going to be?
It's above 7 because it's a weak acid.
Okay, but what number of mils is the equivalence point going to be at?
Sorry. No.
When are they going to be equally molar?
Yeah, 25. No. 12.5 mils.
Okay, so 12.5 mils.
Because that's half of 25.
So your concentration of acetic acid is double the concentration of sodium hydroxide.
Wait,
So
say that
you-
slower.
So your concentration of acetic acid is double the concentration of your sodium hydroxide. So to neutralize it, you're only going to need half the amount. Half of 25 is 12.5.
12 and a half.
Okay.
So what would our titration graph look like at this point in time? So it'd be going down.
Down.
And then we'll
Okay. So if we say that 7 is here, where's that point on the titration curve that we just calculated?
Wouldn't it be down the bottom?
Where is the point?
yeah, like the
lead
leaders
is
just like that.
Yeah.
after the equivalence point.
So it's after the equivalence point, isn't it? So it's probably in this straightaway, but it's after the equivalence point.
So that pH, is that pH like when it's completely reactive?
That's at a point in the reaction.
A point.
Because you can keep, so what you've got is you've got a particular amount of
But like
sodium hydroxide,
all of them have mixed, like once both of them have mixed together.
yeah, in that ratio.
Yeah, in that ratio, that's like the end.
It's past the equivalence point though.
It's neutralized and kept going.
Yeah, it's
Kept adding.
gone past neutralization. So let's work out what the pH is at equivalence point. So at that point of equivalence. Okay? If it's at equivalence point, what does that mean, Rhonda? What does it mean if it's at equivalence, Rhonda? It's neutralised. So not neutralised, that there's equally molar amounts of both, okay?
Wait, isn't that only in equilibrium reactions?
No, it's in everything. It's in titrations as well. So it's 0.1 mole H, we've got 25 mils of that. So our HACET at 0.2 moles, the equivalence point is 12.5 mils. Okay, so if we follow the same logic as we started with before, so let's write up our reaction first. So our reaction is going to be HACET plus NaOH, giving us, I'm just going to call it ACET minus. This time round, we're going to ignore the sodium because it's a spectator, plus H2O.
Stephen, is that little N there, is that molarity or moles?
That's molarity.
Okay.
Okay, so we know we start with 2.5 times 10 to the minus 3 moles of this.
It's the same by definition.
2.5 times 10 to the minus 3 moles of this. So we subtract 2.5 times 10 to the minus 3 moles minus 2.5 times 10 to the minus 3 moles. So we end up with 0 moles of that and that. Agree? Agree? We start with 0 moles of this and 0 moles of this. So how much of those two things must we form, Ben?
2.5 times 10 to the negative 3 moles
So-
for each one.
You would like to use that capital M for moles and molarity. Or
Yeah,
like
you use
not
it for
really?
this.
I try and do moles per litre for molarity.
Right, okay, that makes sense.
It makes more sense. So then we end up with 2.5 times 10 to the minus 3 moles of this stuff in our solution. Cool? Come on, question.
Oh, so because we changed the
So-
amount, so we changed the amount of milliliters,
Yes,
so we can find.
the pH at equivalence point, at the point where we've got equal molar ratios of our acid and base. Got it? Good. Right, next step.
Wait, why did we divide 25 by 2 to get 12.5?
Because it's molar ratio, 2 to 1.
Oh, okay, got it.
0.2 to 0.1. Right, next step, dissociation. Now what's the dissociation going to be of this time round? We don't have any acetic acid, we don't have any sodium hydroxide. So what are we left with? Water doesn't count, acetate. Okay, so we've got acet minus plus H2O is going to give us what?
H acet and OH minus.
H acet plus OH minus. Everyone agree with that?
Yeah.
Okay. Ed, you confused? No, you got it? Good. James, you got it? Yep. All right, so what are we going to do now? What do we know?
You know, concentration of acet minus.
Okay, we know acet minus. So we know here we've got what's our concentration going to be? It's going to be 2.5 times 10 to the minus 3 over.
Over, wait, what are we calculating?
Oh yeah, it would be concentration.
1, 12.5? No, over them together.
37.5. So 0.0375 mils, which gives us a molarity of 6.66 times 10 to the minus 2. Yep.
I was taking on the notes. Where'd that equation come from? The one you drew around? Like the.
This one here, so that's the dissociation equation of the acetate ion, because that's all that's left in solution, and we know it's going to be a strong conjugate base.
If it's an ion, then how's it dissociate?
Well, when you've got water, so what it does is it takes the hydrogen off the water and forms acetic acid and hydroxide ions. Does that make sense, Alex? Has that clarified that question for you?
To the minus 2.
All right.
So do we need to know like a KB for acetate, or do we assume that it's like a lot because it's a strong conjugate base? Like,
Well, we can work out a KB, can't we? So let's just play with this little bit of maths here. Let's just have a look at this for just a second. We'll leave let's leave the concentration of acetate to the side for the time being.
Wouldn't we assume that it's the same on the other side for the 1-to-1?
Nope, can't do that.
Oh.
Can't do that. Okay, so
pH at equivalent.
So we've got this thing here. So if we were to write a KB, because this is a base dissociation constant, if we were to write a KB for this, what would our KB expression look like? Now, what else do we know that KB is equal to? Ka.
Times KW. No, it's something to do KW.
What's KW?
So KW, which is the dissociation of water, is equal to Ka multiplied by KB.
Oh, so it's KW over KA.
Okay.
is 2 plus 7.
KW over Ka.
But do we know the concentration of water?
So we're going to assume that the water concentration is really, really tiny. You don't include the water concentration anyway because it's a liquid. Okay, so what can we do here, knowing some stuff to make our lives heaps easier? So what are our unknowns in this case, Ben?
Oh, no, I just worked out how you could do it though.
Well, how could you do it? Talk to me.
Well, if KB equals that,
Mm-hmm.
and KB also equals KW over KA, KW equals, oh no.
KW is a constant, isn't it?
Yeah, never mind.
Unknowns.
Ignore me.
Hydroxide's
What
an
is
unknown.
KW? Can you tell us what KW is?
10 to the minus 14.
Constant. It's how much water naturally.
It dissociates at 20 degrees Celsius. Okay, so where are we at, ladies and gents? So what's the next step? What can we do with this? How can we play around?
I'd say calculate KB using KWKA.
But what else can you do instead? What else can you do to reduce your amount of time taken to do that thing?
Google it.
No, don't Google it.
Because you
Cool
could.
test, theoretically.
You won't be able to Google it in the test, will you? What would our rice table look like? I did stuff up.
Right.
Okay, so if I erase this and put a rice table in for this dissociation, so let's erase this.
Do we erase that from our book?
I'm going to erase it and we'll come back to it in a second, okay? So our rice table will be 6.66 times 10 to the minus 2. So this is our reaction, this is our initial concentration. We rub out the water because it doesn't take place.
Has no concentration.
No concentration. Our acetic acid is X, is 0 to start with.
Eventually will be X.
And what's our concentration of hydroxide ions in natural water?
10 to the negative 14. Is that
10 to the negative 7.
10 to the minus 7. Okay.
Well, we need to know this for the test, like the.
This is assumed knowledge.
The concentration of the.
Yes, that's assumed knowledge from last year.
Oh, no.
That's assumed knowledge. So what's our change? So our change in this case is going to be
Minus X.
minus X.
If it's not suggested otherwise, should we just assume that the water is in the right conditions for
Yeah.
it?
Yeah. And then it's going to be
Plus X.
10 to the minus 7 plus X.
So, plus that.
Oh.
It's the change is just
Oh, it's plus X, sorry.
Yeah.
And our equilibrium value is going to be 6.66 times 10 to the minus 2 minus X. X. X plus 10 to the minus 7.
Okay, when you said you were making this a little bit more complicated, that was an understatement.
Why? It's not an understatement, is it?
So,
Decently more complicated.
It's decently more.
Fundamentally the same deal.
And because this is really, really small, we can actually not bother looking at the 10 to the minus 7 because it's really, really, the 10 to the minus 7 is going to be really, really small in comparison. It's going to be a strong base. Okay. So, what we now have, right, back to what we had on the board before.
Need more board.
Need more board. I hate this board. It's tiny. It's
How are we
tiny.
going to do it on a test paper?
Get the massive
Which
lecture
is
with the
smaller
sliding
than a board.
sliding board.
You can just use. You can use the approximate. You can use the. You can use the things I'm deriving on the test. Okay.
Use the things on what now?
Use the things I'm deriving on the test. So you can use the KB
What does that mean, things you're deriving?
Like stuff you're
Stuff.
showing where
stuff I'm showing you right now. You can use that on the on the test instead of me having to having to do it. Does that make sense, Kamaya? Gosh, dude, come on. All right, let's go. So KB is equal to concentration of. No, I was not mocking you. Right, which equals KW on KA. Oh. Now, is this going to be big or small, this X value here?
it's going to be quite small.
It's going to be quite small, isn't it? Why is it going to be quite small? Because KA is quite small. Okay, so we're losing not very much. So what we can say is that KB is equal to X squared over
Why can we say it?
this.
Oh.
Minus 2, which is equal to 10 to the minus 14 over 1.8 times 10 to the minus 5. And then we can just rearrange to work out what x is and take the square root of it.
Why don't we know both KW and KA?
We-
Don't have that information?
We do have it, yeah.
So why aren't we just
Well, you could just make KB and then just substitute that in, yes.
okay?
I was making it slightly more complicated than it needs to be, but do you get where we're going? Yep. Know how to punch it into your calculators?
Wait, why'd you make it 10 to the minus 14 over 1 point?
Because that's KW. KW is 10 to the minus 14.
Oh, okay, yeah. So where'd the x squared come from?
The x squared came from that multiplied by that.
Oh, okay.
Alex?
That little X thing next to under the OH minus is not high. What is it?
Isn't the
I can't tell.
Sorry, I can only hear one person at once, Kamaya.
Oh, I think it's just minus.
Is it just a like?
This here,
I can't tell what that says.
that says pH. That's for the graph.
Oh, right. So it's just X.
Yep.
Yeah, I was confused.
Okay, and then from there you can work out what x is.
down the bottom under the 10 to the minus 7, like under the OH, isn't x plus 10 to the minus 7? Not just x?
Yep, but we took it out because it's very, very small.
Oh, okay.
Okay?
So is this just like an approximation?
About 10 to the minus 7. You know, we're talking really small stuff.
Where did the minus x go on the
Because this is going to be really small, you can just get rid of it. You can approximate. It's an approximation.
If x is so small that you can get rid of it, why don't you get rid of it on the other side as well?
Because you need the x. So it's going to make very little difference to that value, but it's going to make a big difference to the actual pH value. Okay?
Taking log.
Yeah, because we're taking the log of the pH value,
So you can take all the x's out except for the one.
except for the x squared.
What is there's a 10 to the power of minus 7?
Yep.
The I, then when you plus x, it becomes x.
Because that's very small in comparison to the amount of base that you're going to get.
It becomes x.
Yep. Okay? All good? Work it out, calculate an answer. I'm done talking to the video.